What's going on, everyone? This is Giovanni, also known as CryptoJoe11, and we are back today for another solutions to the homeworks of the Plutus Pioneer program. Weeks are flying by, and the complexity of the exercise is just simply skyrocketing. We are already at week number 7, I guess, and I fell a little bit behind with the exercise, but today I managed to finish them. I reviewed the code, and now I'm gonna try to show how I solved them and the thinking process I went through. I just want to remind you that I am also stake pool operator, so if you want to support me, my channel and my work, please delegate to the easy one stake pool. And yeah, that's it. Thank you very much. I want to thank everyone for all the feedback that you've been giving me throughout the day and the weeks. I really appreciate that. It makes me feel like it is worthwhile what I'm doing, so I'm gonna keep doing it. And if there is anything that is not clear while you watch those videos, please do not hesitate to post a comment below. I'm gonna try to do my best to answer the questions. Again, I'm still definitely a Haskell beginner, but I'll do my best to answer your questions. So without further ado, let's go to today's this week exercises. So I switched from IntelliJ IDEA to VSCode in the last couple of weeks because upon suggestion of a colleague of mine, I found out that a couple projects integrate very nicely with an extension of VSCode. So this is the reason why I'm using VSCode. But in order to make the suggestions, the auto completion and suggestion to work properly, what we have to do is to start a Nix shell within Plutus at the right commit that is actually used during the week. So let's do one step at a time. If you're interested in auto completion, please let me know in the comments. I'm gonna possibly try to do a video only about how to have auto completion with VS Code and the Haskell. But I'm gonna do this because I have to do that anyway. So this is my Plutus Pioneer Program project. Git pull -- rebase to get the latest version. There shouldn't be anything else because I just did that. I list the file, so I go into code, then I go into week 5, that is the week that we are trying to solve now, and then there is the Cabal project. So the Cabal project is where there are all the Cabal specification for the project. So I'm gonna do less Cabal project, and I do need the checkout of the Plutus project. So I'm gonna get this commit, I'm gonna select and copy, and then I'll just exit with Q, and then I'm gonna go to my Plutus project that is just beside the other one. I'm gonna go git checkout. I'm gonna check out this one. I actually already was on this one, so what I'm gonna do now is open a Nix shell. This should be relatively fast, but if by any chance Nix is gonna start to rebuild, download, whatever, I'm gonna speed up the video. Once that the Nix shell is open, it means that basically all the dependencies required from Plutus have been downloaded, compiled, whatever. So at that point I can, from within the Nix shell, there we go, from within the Nix shell I can go into the Plutus Pioneer program. I'm gonna go back into code. I'm gonna go back into the week 5. And not only at this point, I'm gonna do a Cabal build. This is gonna basically ensure that all the dependencies and all the source or whatever that is used for this specific week is pulled up to date. And only at that point, and this is the one that I wasn't doing correctly up until a few days ago, and thankfully someone corrected it for me, I can actually now run VS Code from here. So this is the full path of VS Code, and then is code that is executable for VS Code and dot. So basically it's running from within this shell and the VS Code. We do need this because there is there's one component called Haskell language server, I think it's something like this one, that basically is gonna be spawned automatically when you launch VS Code, and it's gonna have exactly the dependency for this week of the source code. And so basically VS Code is going to be happy, it won't be crashing, and it's going to show me like the proper correct suggestion. So I'll just do this, and as you can see, magically VS Code is coming up and everything is nicely highlighted. And if I go here, I can have like all the auto completion, for instance, like this. it tells me what there is, etc., etc. In this way, I ensure you that it's ever so slightly easier to complete the class, because that little bit of the IDE helper makes all the difference to me, at least, that I am completely dependent by this thing. Anyway, without further ado, let's get started with the first exercise. So the first exercise is about minting. So what we are doing, this policy should only allow minting or burning of tokens if the owner of the specified public hash has signed the transaction, and if the specified deadline has not passed. So in this exercise, so if you want to know more about this, here is the link to the class, and you will read about the full extent of the exercise. But here, basically, we're gonna just guarantee that whoever signed the transaction can only the owner of the public key that signed the transaction can actually mint the token, and also it has to happen before a specific deadline. So we will have to implement those three functions here. I guess the remainder of the smart contracts, the off-chain part, has already been done by Professor Lars, and so that should be it. I genuinely believe that this exercise is not that complicated, but there is a little bit of boilerplate that needs to be taken, and I'm going to be lazy and I'm just going to be copying it from the class, and then I'm just going to update the things in order to make it work. So because this is something very similar that we've been doing in the past, I'm just going to proceed. Usually we used to have like a validation script that is what is the on-chain part. In this case, it's just the policy. And in here, we will also have to implement the validation part so that we are sure that whoever is actually minting the token is actually whoever is signing the transaction. So I'm going to be using the usual approach of trace if false. As you can see, there is a nice suggestion, missing or wrong signing key, pub key. And then here I'm going to do check chk key. Of course, the method hasn't been implemented yet, but I'm going to do this in 1 minute. Actually, you know what? I'm going to do this now. I'm going to write read the where clause, and then I'm going to do define this thing, the method, the function. It's going to be returning Boolean, of course. And at the moment, I'm going to just implement it as false. And the second thing is trace if false, and the second part of the validation is that the deadline has expired. So oopsie, deadline passed. And also this case is going to be check deadline chk deadline. So this can be either done in line because the two methods are very simple. I still like to do so. So at the moment I'm going to go this way, and I'm just going to do like this. So just statically implement the method to false, and now we have to implement these methods. So we will need to work. So the first thing is that this function is parameterized. So we have the public key hash of the wallet that is actually signing this transaction, is attempting to mint the token. So, and this is the first parameter, pkh, and the second one is the deadline that is defined. If we just scroll down for a second, in the part where we are simulating the interaction with the wallet, we see that the deadline is set to 10 blocks. And basically means that from the generation of this of the script contract, there are 10 blocks within which wallet 1 can generate tokens. After those, it won't be allowed because the limit is 10. After that, this transaction will basically not happen, and won't happen because either the validation of the off-chain part will prevent it, or if the validation of the off-chain part wasn't working properly, the script on the on-chain part, on the blockchain, will actually prevent this transaction to be committed or happen altogether. So cool, let's go back up and let's try to implement this thing. So the first thing that we have to know is that all the information that we need, we don't have a redeemer in this case, but everything that we need is in the context that is of type script context. Of course, the deadline is of type slot, and the public key pkh is the public key hash, and we have to return a boolean. So just to recap, this is a function that takes 3 parameters and returns a boolean. So because I'm really bad memory-wise, let's record to the documentation to remember what this script context is about, and how can we access the information from this context that we do need. In particular, there are two. The first one is the list of the signatories, so basically who signed this transaction, and we will use this information to check the public key that's signing this transaction. The second thing is to take another parameter is the country member that is like the slot range or something like this. And we will use that value to compare it against the deadline, and we will return true or false accordingly. Basically, in this case, if we are within the deadline, we will return true or false otherwise. Script context contains, let's go to documentation, this is going to be easier. So we go into the context, Plutus V1 ledger context. This is, of course, the Plutus project here. I'm going to increase a little bit the font, too much. And then I'm going to be looking for the script context. I'll go through the documentation, and there we are. We're going to be looking at this one a little bit. So the script context, this is exactly the data structure that we are dealing with. And this script context contains two fields that are data structure in their turn. The purpose that at the moment we don't care, and then there is the transaction info. And transaction info is defined up here, and it has all this list of attributes. What we will need, first of all, is the slot range that is here, transaction info valid range. We will use this one to understand at what point of the time the blockchain is, and then the transaction info inputs. So let's do the first part first. So the first thing that I want to do is to extract the tx info. So I need to get this function, this attribute, and use it to extract. So we will do another helping function, and we will call this tx info of type capital TX info, and the implementation is nothing else than that the context, but we get this attribute script context info, and we set it here. You can see that at the moment it's grayed out. It says, look, you've defined this thing, but you're still not using it. So what I'm about to do can be also done in a more elegant way. I can't remember what method is that one, but of course everything works. So I'm going to code this thing live, then I'm going to go back to the documentation, trying the more elegant way of doing this, more and concise as well. But at the moment this is going to work, and so I'm going to go that way. I think there is a method that is that tx assigned by, I don't even know if it's in scope, but I'll do it after. Anyway, let's continue. So I have the transaction info now. Let's go back to the documentation. Transaction info is here. The transaction info is here. And now, I need the signatories. I don't know why I was pointing to transaction info inputs. I need the signatories. This is basically who's signing. Signatories provided with the transaction. So it could be one or multiple. In this case, we just suppose that is only one signatory. So what we need to do is that we need to ensure that the pkh, because transaction info signatory is an array, is a list, we can use the elem, and we use the infix form. So we have to check that the pkh belongs, is included into the transaction info signatories of transaction info. So basically what we're doing here is that from the transaction info data structure, we're extracting the list of the signatories, and then we are checking that pkh belongs or is included into this list. I don't think we need to put any parentheses or dollar, because this should actually be correctly executed and interpreted by the compiler. But we may come back to this if we have some funny business here. The second thing that we have to do is to ensure that the deadline has not expired yet. So basically how we're going to be doing this is that we are going to create an interval using the keyword 2 of the deadline package, and then we are going to check that the slot range of the context belongs to the deadline. So how we're going to do this is the following way. So from the context, we need to get the slot range. I lost it. There we go. Takes info valid range. So takes info valid range of control context. Sorry, I have to do the opposite. I can do two. I need to create the interval first to deadline, and then this one contains, and then contains the slot range that is. Is this correct? Sorry, it's not context, it's tx info, and I can remove the parentheses because also in this case this should work. Right. So we've implemented the first function, we implemented the second function. Those two are defined here. Let's check immediately if this code is correct, if it's compiled. So what we're gonna do now is basically cabal rep, and we open the rep. Also in this case, this should be relatively fast because we've already compiled everything. So what we're gonna be doing, we're gonna be loading the module source week05 homework1 haskell. The model is loaded, reload, everything is fine, it's compiling, everything is good. I just can't execute the test yet because those two methods are not implemented yet. So I'm gonna close all the other one here. I'm gonna be extremely lazy, but because this is boilerplate, I don't find this particularly useful to learn what's going on here, because there is lots of template haskell, Glasgow, no Glasgow, whatever brackets are there. So what I'm gonna be doing is I'm just gonna steal from the what is the signed, that is the one that is most similar. Yes, I'm gonna take this one and I'm gonna be basically copying it here with a difference to pkh. I think this is exactly what we need. Sorry, this is not the correct one. I need two parameters here, so I'm gonna be just stealing the one from the NFT. We're gonna have pkh and then slot, S for slot. We're gonna be passing pkh. Actually here I'm gonna deadline. We're gonna call it with the proper name. Then we call this one pkh first and deadline first. So apology for this, I'm gonna explain in a second. So the make policy function is parameterized twice, so has two parameters, and we will have to specify them when generating the actual policy, the monetary policy function. Because this is parameterized, we will have to use the template haskell, and we will also have to lift code of the two parameters. We have to apply code and lift code for the two parameters. There is a long story behind this one. I'm actually not exactly sure how to explain it, so I'll just, if you want to know more about this, just please refer to the video linked earlier on, where Professor Lars explains why we have to do this. But long story short, what we're going to be doing, we get the public key hash and the slot, that is a value deadline, and then we have to use a lambda function here, where we basically say those two parameters that have been lifted and applied into the code have to be passed into this function in order to everything to work. This is relatively simple, and hopefully this should work. In this case, what I have to do here again is basically just call the this script currency symbol. I have to call the policy, and then I have to pass the two values. And basically, this should be it. And as you can see, there is not much, this part is all boilerplate code, while the genuine juicy part is something that we have already done multiple times in the past, so it wasn't that complicated. So first of all, let's check if, first of all, it compiles. We got a couple of warnings for unused imports, but that doesn't matter. We do the test, and then we see that the deadline was expired for the second one, while the first time the code correctly forged the value. So this looks like this worked successfully. So the only thing that I wanted to say is if there is in scope a function, there we go, the transaction signed by. So as you can see here, the code is quite concise. So technically we could straight away implement this thing inline up here. So the first thing is transaction signed by. Let's see, in is part of transaction info defined in ledger, and it takes a public key, it takes a transaction info, and the public key hash returns a boolean. So let's see if we have the two things. We can use this one here, public key hash. Okay, so if we use the where here, we can use transaction signed by like this, and then we say the x info because we have used the where clause here. Whatever we define here is actually visible up here. So we can use transaction signed by the x info that is visible, and then the public key hash is here. So, and this should actually work, and we can basically ditch this initial part here. I do think though that I have to wrap those two into parentheses so that we make everybody happy. Now, I don't think there is any more concise way of expressing this one thing here. So what we can do is that we ditch this one as well. We open the parenthesis, we slap this one inside, and this should technically work. We have to rebuild the module, usual imports, and then test. Boom, I think it's exactly the same outcome. Rightio, so I think this is the best that we can do. Yeah, let me know if there is anything that is not clear to use, to you all, and yeah, I think it's time to switch into the homework number 2. That, I gotta be honest, I found extremely challenging. So, homework number 2. In this case, there is quite a lot of things that have to be done here, right? But the craziest thing of all is that for the very first time, we have to implement from scratch the contract. So whenever I was trying, as soon as I found this with this thing here, my blood froze, because I was hoping that there would be at least a hint from Lars, just like a little initial push to understand how to start to write this one. But my brain completely froze, and I just couldn't think how to do this thing. So before starting this one, let's do the initial boilerplate part and the usual validation and the monetary policy first up here, and we will think about the actual contract later on. So here we are back into doing NFT, and so you do remember that whenever we are doing NFT, in order to ensure that the NFT is actually unique, there are two things that have to be done. The uniqueness is given by the fact that we use a UTXO as a parameter to the transaction, but at the same time that UTXO needs to be consumed. Otherwise, we could actually just reuse that UTXO again. So that's the first thing. So UTXO of an address of a wallet, in this case a script, needs to be consumed, and this thing, and so the UTXO needs to be a parameter of the function, of the validation function, so that basically the on-chain script is basically unique because this script is characterized by this UTXO. First thing. Second thing, this UTXO also needs to be consumed. Otherwise, we could do another loop of the script, just refer to the same UTXO. The UTXO wasn't consumed, and we can generate again exactly the same NFT again. So this is not going to be an NFT. So the trick here is to refer UTXO as a parameter of the validation script and consume the UTXO. And this is the tricky technical bit. The second thing is that we just have to create one of them. And this is very simple because there is somewhere we're going to just lap one into the thing. The second bit that it's requested by the exercise is that the token name needs to be an empty string. So yeah, this is just a custom requirements. We do remember that there is a that in order to characterize a native asset, we have a currency symbol, a token name, and then a quantity. If it is 1 and it is an NFT, this is a non-fungible token. It is a fungible token otherwise if we have higher cardinality. Right, the usual thing, because I'm learning this thing only recently, I am not gonna try to make the fancy version first. I don't even know if there is a fancy version or concise version to go about this. I'm just gonna take the time to do a first implementation first, and then I'm gonna iterate over it and understand if there is a nicer, easier way of doing this. Sorry, a nicer, more elegant way of doing this. I'm gonna pick up the easier way first, where I'm gonna just basically list all the steps that have to be done here. So at the moment, there are two things that we have to ensure. So the first thing, the easiest thing to do, first of all, is to ensure that the token name is actually empty. In order to do so, we're going to be using an helper function. We call it tn as token name, the type of token name, then we say token name is equal to a token name, but this is going to be an empty byte string. Also, this is not sufficient. This is not sufficient because this function that is going to be used into the validation code, the monetary policy code needs to be on-chain, and so everything needs to be inlineable. Sorry, I have to do tn, not make policy, otherwise the compiler will go nuts. So the first thing is we're going to be using, as I said, the easier approach, trace if false. Token name is not empty, and then check tn and then as usual I'll do my where, and I say that this one is of type bool, and then I'm gonna be setting it to false just to make the compiler temporarily happy. The second thing that I'm gonna be doing is trace if false. This case is outref has not is not included. This really means that it hasn't been spanned. gk oref. And as usual, our little function here false. So it goes without saying that we're gonna take all the information we need from the CTX, from the context. So we go back to the documentation again, because my memory is a sieve. And then in order to get transaction info, this is the name of the attribute, txinfo of type txinfo, and this is txinfo, now little, oh come on, is equals to of this one of ctx. Fine. So this is the first thing, and it is done. So the easier part in this case is to check for the oref. So where are the orefs listed? The orefs are listed, and this is the reason why earlier on I was focusing on this one. We need to ensure that a UTXO is used as input to the transaction. So we need to check that the transaction info inputs contains the oref that we're actually using. So let's check this transaction in info, what is the face, what is the structure of this object. and it's up here actually. And we have that this thing is composed by a transaction txin info outref, and this is exactly txref, the type that we're actually looking for, and then there is txin info resolve that is of type transaction that we don't care. So we do need this one. So what we're going to be doing is, let's go one. So we have a list of these ones, and we need to check if the outref that was sent as a parameter is included in this txin info. So we're going to be splitting this problem into two parts. I know that during the lesson this has been done with the any. There are multiple ways of doing exactly the same thing. What I'm going to be doing is I'm going to take this list, I'm going to map it and just extract all the outref, and then I'm going to be using the lm to check that the outref is part of this list. I think it's easier done than said. So let's do this. I'll take the transaction info inputs from the tx info. So let's do this first thing first. Inputs tx inputs, these of type tx info, and then I'll take this one, and it's gonna have this type here. I'll put it here from transaction info. Now these transaction inputs now, of course, is of this type here, and I want to change this type here. I want to map from this one. I just want to get tx outref. So the way I'm going to be doing this, and I could actually do this in place. So what I really want to do is I want to use map, and then I'll take this list. I'll take this list that is here, and then I only want to get this value. So I'm going to use this function to extract the outref from this object. So basically this one is saying map, take this attribute from this list of object tx in info. So because I have to apply this thing to this result, so this is equals to this one, I can take this one and replace this one here, and I can do all of this here. And instead of having a transaction list info, I'm gonna basically have a list of tx outref like this, orefs, and this is basically gonna be orefs. Orefs is nothing else than takes transaction info, take the input, and then map the list and extract transaction in info outref. And now all that I have to do is check that oref is an lm of orefs. So basically I extracted all the tx outref. It is exactly the same type here. I went from the list, I just took this property from the list, so I have a new list with all the outrefs, and then I can use this one. A different way would be using any. Basically this thing says that loop through the list and check if there is at least one object of type tx in input, of which the property tx in outref is equals to the other one. I think I can even try to do this. I'm gonna call it check outref2, just out of curiosity. Check outref prime, as the professor says. So what basically I'm gonna be doing, we're gonna be taking all the inputs, and then we're gonna go like any, and then I think I need the lambda here, and I think what's the name of tx in info? No, I can use in tx in. So and then I need that this one of tx in is equal to oref, but I'm gonna be slapping this into here, otherwise it won't work. But 1 second here. Do So tx info, and then I'll take tx info inputs is this one. It's returning me a list of tx in info, and then I say if there is any of tx in info, is this a property here? Any foldable able t of a, and third returns a boolean. Foldable, and then the lambda function, and then this thing is, I don't think so, but I'm gonna put this one here. Oh, yes, that's all that wasn't working. So yeah, like this is not recognized because basically I need to extract this property from this object, and this is all that was missing, or alternatively brackets. So this one is done as well. Oops, sorry. I am not exactly sure which way is the nicest. I like to use the map because I personally think it's easier to think about. Alternatively, we could potentially replace this one instead of orefs this way, but we will have to use the brackets here. Actually, the compiler is giving me oh yeah, it's giving me a hint that I can just replace this one here, and this is gonna basically do the trick, and then I can ditch the orefs here that are not needed anymore. So this was a very long explanation, but look, at least we are exploring the different type and different ways we can do this one thing here, right? And now check the transaction, check the token name. This is actually looks simple, but all of a sudden it gets a little bit cumbersome. So the one thing that we have to remember is that we do have we will need the transaction info forge, right? This is basically the famous value. The value is nothing else than everything that needs to be forged within the transaction. Of course, you can only we can only forge tokens. We can't forge ADA, and there can be lots of things in here. But because we are trying to make an NFT, apologies, in this value there must be exactly only one element, and must be the NFT that we want to mint. Now, one thing that we have to remember is that this value is a map of currency symbols to that currency symbol is the key, and the values are a tuple of token name and quantity, right? Let me see value. I can't remember in which package this thing is. Otherwise, we could go to the vLedger v1 value. Okay, Plutus v1 ledger value. So we go here, import Plutus v1 ledger, and then is okay. Import Plutus v1. What's wrong with this? There you go. And then I need values. I think it's, oops, I always do that. There we go. So we ask for information about value, and value is nothing else than a map from currency symbol to a tuple of token name and integers. Boom, as simple as that. So what we need is basically to ensure that in this map there is only the NFT that we want to mint. So let's and this value of course is in the context. So let's go and get the also what we want to do, right? This is going to be, I think so what we're going to do, the approach, the logic is going to be this one. From the transaction info we get the info forge. value is a map and it's complicated to work with maps. So what we're going to do is also we're only interested in the first thing that we're going to do is basically we're going to extract the keys of this map, and we have to ensure that there is only one key. And once that we get that key, we ensure that the value of that key is exactly the token that we're trying to mint. And also in this case, I think doing it is going to be easier than actually saying it. So what we're going to do though, we're going to use the case of, because we're going to do some sort of pattern matching, and there are going to be two situations. The first one is exactly the one where there is only one key, one value, and then we check that the value is exactly a token name with the empty byte string and the value 1. Any other case is going to be false. So case map, keys of, now I have to take something from the x info as the info forge. I don't think I can do forge. If I do like this, the x info forge, is that thing? Yes, it's exactly it. The x. Oh, come on. There are two cases here. Then there is the case of there is exactly, and this is like the cumbersome part. There is all exactly like CS, the n, and the amount. Actually, I can put 1 straight away here, and then the validation here is that I can't use the n, I have to use the n prime is a CS into context. Actually, do I care about the currency symbol? I don't think I care about the currency symbol. Do I care about the currency symbol? I'll put this one here. And then all that we have to do is that tn is equals to tn prime. Otherwise, what happened? Back here. Otherwise, it's false. And I guess that I need to do something like this, because otherwise this won't work. I need to fix this one. And then what's telling me? Redundant bracket. Found case map case of tn. Why not? But is there an error? Yes, there is an error. Map keys. There we go. I made a mistake. I made a mistake because this is a map. No, sorry, I made a mistake. I don't need the keys here. I need to flatten. I need to flatten value. I need to flatten the value. Yeah, sorry. I'm confused. And I need to flatten this one because I told you is a map, and then there is a function that is flatten value. Yes, I need to import it. Thanks, Cabal. Basically, what it's gonna do? What it's gonna do is from a map is gonna just return me a list of two tuples so that I can do the case of onto this one, and this is gonna help me. This is gonna help me do the pattern matching in an easier way to check the constraints. But there is something that I'm not sure. Could not match transaction info. Oh yes. I think that I just have to do, is that possible? I have to do something like this. There you go, much better. So I take the value from the transaction info, I flatten it, and all that I want is that if I can pattern match against this one, so I don't care about the currency symbol, I do care about the transaction name. Again, I'm gonna call tn prime because I'm already using tn here. And then I'm saying pattern match also against the amount and needs to be 1. If, for instance, the actual value that is in here is 2, it's gonna fall into this one. And then all that I want is to ensure that this one is this one. I'm not sure if I can actually just say tn here and put true. I can't. I think there is a different way I can do that, but let's say that what I'm happy with is like extract this thing and ensure that the token name is actually matching the token name here, that is the empty byte string, and everybody's happy. So check token, we did it. Check oref, we did it. So let's go and check if this thing is actually compiling. So load module, source week5 homework 2. Boom, this worked. So monetary policy is done. Let's do, as usual, the boilerplate code. The boilerplate code, we take it from the previous exercise. This is going to be a little bit different from what we've done, but doesn't matter, we'll fix it. And we only have one param. This is going to be called oref. And we can delete the second one. And actually we're going to use function composition, and we just have to do script monetary policy. We put a nice dot here, and then we delete everything else. And then again here, this is going to be make monetary policy script policy. And then I can put the dot here. No, what is the symbol of ref? Is that something like this? No, there was a trick for doing this. Nope. Script currency symbols. Sorry, that's the reason why it's not working. And then I can put the dot here. Again, I'm using function composition because the input here is automatically passed into policy, and then with the result is going to be put into this one. Right, let's check again. And I think there are no errors for the moment, I think. So we can proceed with the implementation of the contract. I'll take a quick break and I'll see you in just a minute. Right, and we're back. Before proceeding with the implementation of the smart contract per se, there are actually a couple of things that we have to fix. So this pattern matching here is wrong. I need to explicitly specify the amount here. So this is going to be the amount that needs to be 1. I can't put 1 straight away here. And the second thing is that it's a silly mistake to say, but we need to check the currency symbol, because otherwise we could be minting basically anything, and we actually we need to ensure that the currency symbol here is exactly the one generated by this script. It's a little bit of a chicken and egg thing, but as explained into the lesson, there is actually a facility method, the utility method, that allows us to fetch straight away our currency symbol of the function we're actually implementing. So CS is going to be the currency symbol here, and basically what we can do is I'll put a couple of ampersand, and then there is a function called own currency symbols that takes a script context that is the CTX, and it's basically as simple as this one is to be equal, of course, to CS. And basically this is going to be the validation. If we reload the script, the code, everything is compiled properly, and we are happy and good to go to the next phase. So we have done the facility, the utility methods, we've done monetary policy, we've done the currency symbol, and now it's the the actual contract. So before starting, I think it's important to, before diving straight away into the code, I think it's important to have like the so-called pen and paper approach that my professor back in the days in the college, almost 20 years ago, was teaching us. Of course, I can't do pen and paper here, but we're gonna just like type the fundamental steps that we have to take here. So the objective here is to mint a token. So we definitely need the value. The value in the sense of the of Cardano. So what's it called? The currency symbol, token name, and the quantity. We want this the value to be forged as part of the transaction. We want a specific UTXO to be spent. And in order to be spent, we have to find the UTXOs. And then we have to build the monetary policy from the UTXO. So we have to create monetary policy from the UTXO. Then we have to build the transaction, and then we have to execute the transaction, and then wait for the result. And in terms of constraints, we have to spend UTXO, forge the value, right. I think this is the beginning. Right. There is one extra step that we have to do. UTXO to be spent. Let's spend 2 minutes to speak about the UTXO. In order to get the UTXO, we need the address, and from the address we need our own pub key. So the chain is this one. Pub key, our own pub key. We can generate addresses, and then from the addresses we can fetch the UTXOs. Now I do remember from the lesson that we can use something called the UTXO at or UTXOs at. I'll ask the compiler to help me. That this one returns a map, and this map contains UTXOs where the key is UTXO out ref, the OREFs that we need. One of these at least. If we have one, we can proceed and make the transactions, and this is the one that we have to spend. So I do think that everything starts from here, because this is basically the entry point. We get the pub key, we generate the UTXOs. If we have at least one, we start to create the monetary policy, the value, and everything else. Then we do the lookup for the monetary policy, we build the transaction, we set the constraints, we execute the transaction, and we get the result. Boom, we have a plan. Let's do it. So we are working with monads, and in order to concatenate the steps within the monads, we have to create a do block. Right, so this is the very first step. Thank God we do have the auxiliary contract, the contract object that we can invoke to get stuff. So we do need the primary key, our own primary key, and we can get it from the contract that has a method called onPubKey. Now from the pub key, I think we have a way of getting the OREFs straight away. I think we can use UTXO at. UTXO at, this is the one function that I remember from the class, gets an address and returns a contract with the UTXO map. So what we're going to be doing here, so in order to get the address, we can get the an address from the pub key. And I think the method is pubKey address or something like this. So UTXO at address pub key address. It gets a pub key and return an address here on the left. So I'm gonna do this, and the pub key is the PK, and we have it here. Now what we have to do, what's wrong here? Yes, ignore the error. What we have to do here is to check if the OREFs is empty or is full. We need at least one, and we have to get it from this map. because we don't care about the values. Look at the UTXO map. We don't care about the values, but the keys are are ORFs. Sorry, that's what I mean. So what we're going to be doing is write a case class, case pattern match, case of. Case, we're going to be getting the map, the keys of the ORFs, and then we're going to match against two cases. The first one is that it's empty, and then here we do contract log error, no UTXO found, contract. Is this because I have to write string? Yes, awesome. And then here there is ORF, and I think I can use this notation to say just give me one, and then if it's the only one and there is other or there is nothing, whatever, just give it to me. And then here I can start a new do block to continue the one a new do block. So in this case though, I need first of all to create some variables. Let my value v equals singleton, so currency symbol. The currency symbol requires the UTF-8, so we can do core symbol of ORF. The token name should be TN, and the integer and the value should be 1. Yes, so we can still ignore that thing. Then we need lookups, and here basically what we need to do is to create the validation script, the make policy script. So constraint monetary policy. So the monetary policy here is again a call to the function policy and the outer f. What is it? Then we have the transaction that is composed by two constraints, that is forge, must forge currency, and I think, can I pass monetary policy hash token name integer? Can I pass the b? And then constraints must spend pub key output. This is exactly what we need, is the ORF again, and this should do the trick. Then here what we want is then we need to construct the transaction, submit transaction with transaction constraints with the script lookup is the lookup, and then here is the transaction. I do know that this is gonna return basically so let's see, some transaction with the script context, script purpose, script context. I think this is, I can call it transaction anyway. And then the next thing that I want to do is to await transaction confirmation, the transaction ID that is the transaction above. This is gonna return contract of which I don't want the result. What is the reason here? So await transaction confirmed is transaction ID and returns a contract. Ooh, hang on a second now. Do I need to do TXID? Now this one. This looks good. Right, there is a little typo somewhere, and I think it's because I'm using the auto completion. The must forge is must forge value, not must forge currency, and there is a reason of all the errors. So let's fix things around. So the next thing here is that we need to delete the value. We need to add the void here. I'm not exactly sure what it's doing here, but it's in the class as well. I think it's for the type returned from the lookups. Transaction here was okay. This is there are two things with the same name, so we're gonna be renaming this one with the transact, just a shorter name. So then we're gonna be waiting for this one, and then the last step is contract log info at string success. So this should conclude the code. Let's load. Actually, we're gonna quit 1 second. We're gonna go back in so that we don't have conflict with the other homework. This is compiling. Jesus, this is great. Load code source week 5 homework 2. And then we launch test. Right, we have an error. Constraint resolution error. So constraints resolution error, TX or FAT not found. Not found. This looks like something wrong with the lookup. Let's see into the exercises of the NFT. Symbol. Okay, constraint unspent outputs. Let's see if this one is gonna fix this. I have no idea what this thing is doing. UTXOs, this is RFs. RFs? What do you want? Oh, right. Sorry, I can't use this one here. Let's use this one. Boom, RFs. Reload. And then test. Right, this looks better. This looks better. Different monetary policies. Everyone has its own. So yeah, this looks like it worked. I gotta be honest though, I don't know what is this unspent outputs RFs. Let's see if the documentation says something. Which method is this one now? Constraints. Constraints is part of ledger constraints. Doesn't say much. Ledger constraints off chain. Just constraints of chain. Script lookups value that uses the map of unspent outputs to resolve input constraints. Script lookups value that uses the map of unspent outputs to resolve input constraints. Okay. I think this is just fetching all the UTXOs. Yeah. It's just fetching all the UTXOs. Right, so the lookups here, there are two lookups. The first one is to look up all the RFs, because we must spend this one. And the second one is to fetch basically the monetary policy scripts. There we go. Okay, so we were putting a constraint on the RF, but the contract, the submit transaction didn't have a reference to the RFs. That's the reason why we need this one. So we must forge the value, and then we basically must give the monetary policy, and then we must spend the output, but we need to provide the list of the RFs. So basically this is passing the UTXOs to the unspent outputs, and it's basically building the lookups. And this void needs to be set here in order for the values of the lookup to not interfere with the contract signature. And this did the trick. This was a little bit more complicated than I thought. It is the first time that I, kind of second time, because I resolved this one by myself, and then yet at the same attempt I still made a few mistakes. In symptomatic of the fact that this ain't easy. But I'm glad we made it. It was a little bit confused, but I hope that the process that I followed, the way I structured my thoughts and I put them down, that makes some sense to you. If you have any feedback, please let me know in the comments. Let me know what you think about this, and if you've done things a little bit different. Yeah, thank you very much. Press the subscribe button, hit like if you like the video, and just want to remind you that I'm a stakepool operator. If you like the work that I'm doing and the content I'm creating, please delegate to my stakepool. It's called Easy One. This is gonna help me creating more content and going on and proceed with my studies. Cool, cheers, thank you very much, and I'll see you next time. Bye.